So this time around, we are required to find the value of I of t and I of x of t. That would be I of t, I of x of t. Assuming that I naught is equals to 10 amperes. Recall we are doing the natural response of an RL circuit, and we need to simplify the circuit so that it looks something like this. So that looks something like this, and the way to do this is simple. We can just disconnect this. Recall how we did it with superposition theorem, Norton and Thevenin's theorem. We just disconnect this, and we apply a test voltage of 1 volt to across the terminals, and that will look something like this. And we can simply do our calculation using mesh analysis. If we call this the first mesh, I will call this the second mesh. The current there will be I2. If you write an equation in mesh 1, you would have it that 2I1 minus 2I2 minus 1 equals 0. That means 2I1 minus 2I2 equals 1. We can call this our first equation. Then we can proceed to mesh 2. And proceed to mesh 2, and in mesh 2 we can write 2I2 minus 2I1 plus 4I2 plus 3I equals 0. Now, one thing you want to know is that I flows in this direction, so I is equals to minus 1. So we can write that as 6I2 minus 2 minus 3I1. That will be minus 5I1 equals 0. We can call this our second equation. We solve these two equations simultaneously. We arrive at the value for I1 to be 3, and we arrive at the value for I2 to be 2.5. Now, what we're actually interested in is the value of I1, which is the current that flows like this. That will be I1, and the Thevenin resistance of this entire circuit, like from across this point would be 1 over I1, that is voltage over current. So that would be 1 over 3 ohms. 1 over 3 ohms. So we can come here and say that we have 0.5 henries on this side, and we have 1 over 3 ohms on this side. Now, with this much information, we'll be able to calculate the time constant tau for this RL circuit, which is L over R, and this is going to be 0.5, which is also 1 over 2 over 1 over 3, and that would be 3 over 2 seconds, or 1.5 seconds. And recall that I of t in an RC circuit is I naught e raised to power minus t over tau. So this infers that I naught, which is 10 amperes, I of t is equals to e raised to power minus 2t over 3. We know that this is the value for I of t. Now, this brings us to the next part of the question, which requires us to find the value of I of x. Now, if you look closely, you realize that this inductor and this resistor are connected in parallel with one another, and that means that the same voltage runs through them. And we know that we can calculate the voltage across the inductor. The voltage across an inductor would be V of t would be equals to L di dt, which infers that we know that our L is 0.5, and I just have to differentiate 10 e raised to power minus 2 over 3 t. So we just have to differentiate this with respect to t, and that would give us 0.5 multiplied by minus 2 over 3 10 e raised to power 2 over 3 t. And with that, we know that the voltage is going to be 10 over 3 e raised to power minus 2t over 3. We can then just proceed to find the value of Ix by using Ohm's law to divide by 2. So we know that Ix is going to be equal to Vx over R, and this is the value of Vx here, so that is going to be equal to minus 10 over 3 e raised to power minus 2t over 3 divided by, what's the resistance? That is 2. So divided by 2, and we are going to have minus 5 over 3 e raised to power 2t over 3. And that means that I is equals to minus 1.667 e raised to power 2t over 3, and that is the value of Ix.